The objective of this presentation is to define crystalline solids and explain their basic characteristics. Second, to describe the orderly arrangement of particles in crystal structure. Third, to study the arrangement of ions in ionic lattice lie in NaCl and CHCl. Lastly, to compare giant molecular structure based on their bonding and properties.
Hi, I'm Izati and I'm going to introduce to you to solid. So we all know that solid is one of the state of matter, right? Because it is. But all the state of matters have their differences and characteristics. But today we will mainly focus on solid matter. First, solid particles are arranged closely in a regular, rigid order. While it cannot move freely without disrupting the whole structure, the particle can only vibrate and rotate in its fixed positions. Speaking of fixed, solid matter has a fixed shape and volume. And last but not least, the attractive force in these particles are very, very strong. Next, solid composed of two types of arrangement, which is crystalline and amorphous. First, the condition for a material to form a crystalline solid are that it needs to undergo slow cooling, have a stable temperature and pressure. Next, the material must have a uniform particle size and bonding. And last but not least, it also needs enough time for nucleation and crystal growth. When the conditions are met, crystalline solid form with distinct characteristics, which is the arrangements are highly ordered and regular, a sharp melting point, and definite heat fusion. It's also an anisotropic, which means the properties vary depending on the direction measured. Some examples of crystalline solid are salt, sugar, and diamond. Next, for amorphous solid, the condition for material to form is to undergo pinching. Pinching is basically rapid cooling and a sudden change in temperature and pressure. It must have a complex or irregular particles. And lastly, it was given sufficient time for crystal growth. Here are the characteristics when amorphous solids are formed. It has disorder and irregular arrangement. It melts over range of temperature. It has no definite fusion, and it's an asymptotic. It means it has uniform properties in all directions and orientations. An example for it is plastic, glass, and wood. Here are the important terms that you need to know regarding this topic. First is unit cells. It is the smallest part of crystal, a basic building block of the crystal lattice. Second is the lattice points. This is a point that marks the exact position of atoms, ions, or molecules that form a repeating order pattern called crystal lattice. And lastly, a coordination number. It is the number of atoms nearest neighboring atoms or ions. The larger the value, the closer the spheres are to each other. It is to indicate the crystal stability, packing density, and physical properties.
This is simple cubic structure. Atoms are only at the corners of the cube. The coordination number is 6. An example is polonium. Next is the body-centered cubic structure. Atoms are at the corners and one at the center. The coordination number is 8. Example are sodium and iron. Next is the face-centered cubic structure. Atoms are at the corners and the center of each face. The coordination number is 12. Examples include copper and gold. And for the counting particle, corner atoms contribute 1/8, edge atoms 1/4, face atoms 1/2, and center atoms contribute 1.
Next, I will present the following content, which is the types of crystalline solids. There are 4 types of crystalline solids, which are metallic, ionic, covalent network or giant, and lastly molecular. Metallic solids have a simple crystal structure where identical metal atoms are held together by metallic bonds with delocalized electrons that move freely, making them good conductors of heat and electricity, malleable and ductile, with metallic luster such as copper, gold, and silver. Metallic solids can form different types of crystal structures, mainly body-centered cubic, face-centered cubic, and hexagonal closed pack. In a BCC structure, there are 8 atoms at the corners contributing 1 atom in total, and 1 atom at the center, giving a total of 2 atoms per unit cell with a coordination number of 8. While in FCC structure, 8 corner atoms contribute 1 atom and 6 atoms at the face centers contribute 3 atoms, resulting in a total of 4 atoms per unit cell with a coordination number of 12. And the last one, in HCP structure, atoms at the top and bottom corners contribute 2 atoms, atoms at the top and bottom faces contribute 1 atom, and 3 atoms are fully inside the unit cell, giving a total of 6 atoms with a coordination number of 12.
This slide explains ionic solid. Ionic solid consists of positive and negative ion held together by strong electrostatic attraction. Because there are no electrons, they are insulated in the solid stage. Ionic solids generally have hard melting point, are hard but brittle. They are conduct electricity when more or dissolved in water. One example, sodium chloride, NaCl, is made of Na and Cl ions and a phase central cubic structure. The coordination number is 6 to 6, and each unit cell contains 4 sodium ion and 4 chloride ion. NaCl do not conduct electricity because the ions are fixed in position. Another example is cesium chloride. CaCl is a consist of Cs and Cl ion arranged in simple cubic structure with an 8 to 8 coordination number. Each unit cell contains of 1 cesium ion and 1 chloride ion. Like NaCl, CaCl do not conduct electricity in the solid stage. Next, I will explain about covalent network solid, which are also called giant covalent solid. In this solid, atoms are held together by strong covalent bond in a continuous network. Diamonds are graphite or carbon allotropes, meaning they are made of the same element but have a different structure. In diamond, each carbon atom bonds 4 other in a tetrahedral structure, forming a strong three-dimensional network. This makes diamond very hard and unable to conduct electricity. In graphite, each carbon bonds to 3 other, forming layer hexagonal structure. The layers can slide over each other, making graphite soft, and the presence of free electrons allow it to conduct electricity.
For conclusion, crystal structure influence the physical properties of solids. Different atomic and ionic arrangement in metallic, ionic, and giant molecular structure lead to differences in properties such as hardness, strength, and electrical conductivity.